Okay, so now I'm back. There's time limit on these videos. So now that I'm back, the T distributions are based upon degrees of freedom. This is where I'm going to review how we find degrees of freedom. Could be a really easy question that we ask on quizzes or tests. The entire area of the curve is 1. So sometimes that helps us find some values. But the degrees of freedom are found by doing the sample size n minus 1. And that's exactly why up here, that as sample size increases, so does degrees of freedom, because degrees of freedom relies on your sample size. So both sample size and degree of freedom will help make that standard deviation go down. And like we've already said, that as degrees of freedom increase, the T distribution becomes thinner and taller. So it becomes more tall and thin. And the shape approaches the shape of the standard normal curve. Okay, one thing I want to point out is that it approaches. Okay, there is never going to be a time that your T distribution will equal the standard normal curve, which is also known as your Z distribution. Okay, so it can never equal. So never equals. Okay, so let's show you a little bit more. We remember back in a previous unit, we took some normal distributions, uniform, skewed, all of that. We took a little tabs out of bags. Well, I took one of our class's data for normal distribution when you were taking a sample size of 5. That's when you had these nice little tiles and you drew 5 of them out so many times and put your X's up on the Elmo. So what we're going to do is just take a class set of data just to kind of standardize this among all class periods. So we are going to talk about the normal curve and we're going to take some values out. So first of all, I'm going to tell you that I did count up these X's for you, because I'm so nice. There's 138 X's. So we know that there's 132 or 138 data values. So we're going to take another 5 out. So I'll do that, shaking it up, mixing them, making sure I get a nice random sample. So there's 1, 2, 3, 4, and 5. And I'm going to record these values right here. So I have 45, 54, 50, 55, and 53. Okay. So if I wanted to find my mean, you could use your calculator for this, but I'm just going to add them up and divide by 5 since there is only 5 of them. To get my X bars, remember this is another sample, hence why you see X bar and not mu. So I have 45 plus 54 plus 50 plus 55 plus 53 divided by 5, and that's how I get 51.4. So if I place my X on this distribution, let's see, 51.4 would be somewhere around here. So that's where I'd add my nice little X to that. And let's go ahead and flip the page and talk about what this means for us. We'll kind of flip back and forth for this part. So based on the values already on the distribution, we're going to find the likelihood of getting a mean as extreme or more extreme. So or more extreme than your sample from step 2. So we're going to divide the number of X bars greater than or equal to our X bar value that we found in step 1 by the total number of X bars in the entire distribution. So that's why I told you that there's 138 X's already there. And actually, I'm lying to you. Now there's 139. Thanks to me adding our last sample together. So let's see here. I want as extreme or more extreme. So I want my value of 51.4 or more extreme. So let's see here. If I count that up at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 17, 18, 19, 20, 21, 22, 23. Got 47, and hopefully if anybody's double checking me on that, I'm right because If you're watching this video, you can't correct me since it's not live. Sorry, guys. So dividing those two to find my proportion is 0.338. And that actually represents my p-value. Okay, that's something we're going to have as our evidence for this unit. So let's say we took a sample of size 5 and found that x bar was 56. So looking at the distribution, so our x bar value was 51.4. Okay, if we get 56, which is right here, we want that or more extreme. Do you think that the p-value is going to be high or low compared to our previous p-value? Hopefully you guys are saying low. Okay, there's only one x above that, right? And if you want proof, I can show you, right? To find this p-value, I would count up the x's that are at or more extreme that value, which is just 1 out of 139. So if you divide 1 by 139, I only get 0.007. So hopefully you can see that it'd be lower. So likely or unlikely to get something greater than or equal to 56, that percentage, guys, is barely, not even 1%. So hopefully you know that it's unlikely, okay? It's very, very unlikely. Now, we do have a value to compare this to actually know for sure. Remember that 0.007, which is my p-value, we can compare to alpha, which is our level of significance. So that's less than or equal to alpha, which is 0.05. That's another way you can tell that something is unlikely with evidence. Okay, then we have an x value or an x bar value of 53 is roughly 3 standard deviations above the mean in the t distribution. So we would say that our t value is 3. Okay, so just to show you what I'm talking about there. So if I go to 53, so it's 51, 52, 53. So if I have an x bar of, you guys can't see this, sorry. If I have an x bar of 53, that'd be a t score or t value of 3. It's like being 3 standard deviations away from the mean. Okay, so if I had 51.4, we'd probably say that's about 1.4 standard deviations above the mean. And remember, anytime you talk about that, always say above or below. Okay, then one more on this before we refresh you on p-values. If I told you that I took a sample of size 5 and found that x bar is 58, would you believe that it came from the same distribution of phone chips that we have? So look where 58 is, guys. So 58's right there. There's no data after 139 x's. There's no data at 58. So do you think that 58 could have really came from our sample? Probably not, right? So it's probably not. So it's unlikely that it came from the same distribution. I'm not saying for sure, but looking at our data, how it falls for 139 data values, very, very unlikely that's going to come from the same distribution. That's kind of what the p-value is proving to us. So let's talk a little bit more about this p-value. A p-value is the probability of attaining a test statistic the same as calculated or more extreme. That's literally what I was showing you up there. We went at that x value, and went more extreme. And that's, of course, assuming that our null hypothesis is true, okay? And the way that p-value is found is just the area in that tail. So if I say greater than or less than, remember that those are one-tailed tests, okay? And if it is greater than, that'd be the same thing as me saying the alternative is mu is greater than the hypothesized value. And that's why we went to our t value. So that's our t, and we shaded more than. But if our t value was negative 1.645 and we are doing a hypothesized value where mu was less than that, then you shade into the left tail. Okay, but there is one more test. There's a not equal to. So if I do not equal to, that is our two-tailed test.